The floor of Harold Messing's old spruce log cabin cracked for the last time on the morning of January 9th, 2019. Not dramatically, not all at once. It was a low, grinding sound, the kind that travels through your boots before it reaches your ears. And Harold, 71 years old, a retired civil engineer from the Army Corps of Engineers, a man who had spent the better part of 3 decades calculating load tolerances for bridges and culverts across the Alaskan road system, knew exactly what he was hearing. He had heard the sound before in structures he had condemned. He had never expected to hear it under his own feet, in the place he had decided to spend what he called, with the dry precision that is a mark of his profession, the remainder of his operational years. The cabin had been built in 1987, the year Harold first came to Alaska. He had not built it himself. He had bought it from a trapper who was moving to Wasilla, and at the time it seemed solid enough. Hand-hewn spruce logs, 8 inches in diameter, double-stacked and chinked with fiberglass rope and caulk, sitting on a continuous concrete perimeter foundation that the trapper had poured himself over one summer. It was 480 square feet. It had a cast-iron Joule wood stove in the center and a single-pane window on the south wall, which Harold replaced with a proper insulated unit in his first winter when he realized that single-pane glass in a -40 environment is less a window and more a refrigerated air dispenser. For 22 years, the cabin served. It was never comfortable by any standard Harold would have applied professionally, but it was adequate. He burned between 1 and 1.5 cords of birch per month through the 5 coldest months of the year. The internal temperature during those months, measured with a calibrated Fluke digital thermometer, he kept mounted on the center post, rarely exceeded 58 degree F, 58 degree F. 58 degrees Fahrenheit, when the stove was actively fed every 4 hours. During the 8 hours he slept, the temperature dropped as low as 38 degree F, 38 degree F. 38 degrees Fahrenheit by morning. He adapted to this the way men of his generation adapt to discomfort. He wore wool socks to bed and did not complain. The foundation was a structural problem he had always known he would eventually have to face. The perimeter foundation was bearing directly on mineral soil that sat above a layer of discontinuous permafrost. Every spring thaw introduced water into the soil column. Every winter refreeze pushed the foundation slightly upward, what engineers call frost heave, a phenomenon produced by the volumetric expansion of water as it transitions to ice, which exert an upward pressure that can exceed 50,000 pounds per square foot in saturated fine-grained soils. Over 22 years of freeze-thaw cycling, the north corner of the foundation had risen approximately 4 inches higher than the south corner. The floor joist, which had never been engineered for differential settlement, had absorbed this as increasing shear stress across their midspans. The crack Harold heard in January 2019 was a failure of the center joist, a 2x10 Douglas fir member that had been slowly torquing for years. He drove to Wasilla that week, bought a composition notebook at a hardware store, and began what he described to us as the engineering process I should have started 30 years ago. He was not interested in repairing the cabin. He was interested in replacing it with a structure that the ground could not destroy. Harold Messing is a compact, deliberate man. He has the habit, common to structural engineers of his generation, of pausing before he answers a question, not from uncertainty, but from a practiced discipline of not saying anything he has not already thought through completely. His hair is white and close-cropped. His hands are large and calloused. He drinks black coffee from a thermos. He refills at 6 in the morning and does not refill again. When we asked him why he chose the Quonset arch form over a conventional replacement cabin, he said, "Because I know what soil does to flat foundations, and I know what a catenary does to a load. And I wanted to stop fighting the ground and start using it." The catenary, the natural curve that a chain assumes when hung freely between 2 points under its own weight, is the geometric basis of the arch. A true catenary arch distributes all applied load as pure compression along its curve, with no bending moment at any point. The semicircular arch used in Quonset construction is an approximation of the catenary, not a perfect catenary, and so it does experience some bending under eccentric loads, snow accumulation concentrated on one side, for instance, but the structural efficiency remains vastly superior to a rectangular frame. Harold understood this intuitively from his bridge work. A properly loaded arch does not fail by bending. It fails by buckling, and buckling requires a degree of lateral instability that a properly anchored arch, embedded in bermed earth, almost never achieves. But the arch form was not Harold's primary engineering concern when he broke ground in the summer of 2020. His primary concern was the foundation. Specifically, how to build a foundation that would remain thermally and structurally stable on ground that was actively trying to destroy anything placed on it. The solution he developed, refined through 4 months of calculations in that composition notebook and 2 conversations with a retired geotechnical engineer in Fairbanks, is what he calls a floating thermal slab. And it is, in our assessment, the most technically sophisticated element of his entire build. The core problem with any foundation in discontinuous permafrost country is that you are managing 3 simultaneous and competing forces. The first is the load of the structure above, which pushes downward. The second is frost heave, which pushes upward with enormous and unpredictable force during freeze cycles. The third is the thermal differential between the heated interior of the structure and the ground beneath it, which, if not managed, will warm the permafrost, cause it to thaw, and produce differential settlement as the thawed soil compresses under load. Conventional foundations attempt to manage the first force and ignore or fight the other 2. Harold design manages all 3 simultaneously. The floating thermal slab begins with excavation. Harold excavated the entire 24 by 48-foot footprint of his planned structure to a depth of 36 inches, 3 feet below grade. This removed all the frost-susceptible silted soil from the load-bearing column and brought him down to a layer of coarse glacial gravel that the Matanuska Valley sits on in abundance. Coarse gravel does not retain water in the capillary spaces between particles. Water drains freely through it. A soil that drains freely cannot produce frost heave, because frost heave requires saturated soil, water held in place long enough to freeze and expand in the direction of least resistance, which is upward. He then installed a French drain system at the perimeter of the excavated footprint, a 4-inch perforated pipe laid in a bed of wash gravel, wrapped in filter fabric, sloped at 1/4 inch per foot toward a daylight outlet on the downhill side of the site. This perimeter drain is the first line of defense. Any water that enters the gravel column from surface infiltration during spring thaw is intercepted and removed before it can saturate the soil column beneath the slab. On top of the coarse gravel subbase, Harold installed 4 inches of Type 9 extruded polystyrene foam board, the closed-cell high-density variant rated for below-grade use. This is a thermal break. It is a layer that physically separates the heated concrete slab above from the soil below. The thermal physics of this break are not complicated, but they are worth stating precisely, because this is where most owner-builders make their critical error. They insulate their walls to R30 or R40. They spray foam their roofs, and then they pour a 4-inch uninsulated concrete slab directly on the ground, and wonder why their floors are cold and why their fuel consumption does not match their calculations. Heat moves through materials in proportion to the temperature differential across them, and inversely in proportion to their thermal resistance. This relationship is expressed by Fourier's law of heat conduction. Q equals K delta T, Q equals backslash frac K backslash delta T, Q equals dK delta T, where Q is the rate of heat transfer in BTU per hour, KK. K is the thermal conductivity of the material in BTU per hour per foot per degree Fahrenheit. A is the cross-sectional area in square feet, delta T backslash delta T. Delta T is the temperature differential across the material in degrees Fahrenheit and DD. D is the thickness of the material in feet. For an uninsulated concrete slab, the KK. K value is approximately 0.54 BTU/HR/FT/degree F. For 4-inch slab, D equals 0.333, D equals 0.333. D equals 0.333 feet, with an interior temperature of 68 degree F, 68 degree F, 68 degrees Fahrenheit, and a subgrade temperature of 28 degree F, 28 degree F, 28 degrees Fahrenheit, the stable year-round ground temperature at 3 feet below grade in Harold's location, measured with a buried thermocouple during the summer before construction, the delta T backslash delta T. Delta T is 40 degree F, 40 degree F. 40 degrees Fahrenheit. This gives a heat loss through the uninsulated slab of Slab equals 0.54 times 1152 times 400.333 is almost equal to 74. 700 BTU slash HRQ underscore slab equals backslash frac 0.54 backslash times 1152 backslash times 40.333 backslash approximates 74, 700 backslash text BTU slash HR. Slab equals 0.33 30.54 times 1152 times 40 almost equals 74,700 BTU slash HR. That is a theoretical maximum under ideal steady-state conditions, and real-world conditions are more complex, particularly the role of the soil's own thermal mass in moderating the loss. But the order of magnitude is correct. An uninsulated concrete slab of this footprint loses heat at a rate roughly equivalent to leaving 12 residential exterior doors wide open simultaneously. Harold's 4 inches of Type 9 XPS foam has an R value of 20 per unit thickness, or R equals 20, R equals 20. R equals 20 for the 4-inch assembly. The concrete slab above it has an R value of approximately 0.32 for 4 inches of thickness. The total assembly R value is 20.32. Applying the same formula. Kinsulated equals A times total equals 1152 times 40 20.32 is almost equal to 268 BTU slash HRQ underscore insulated equals backslash frac a backslash times backslash delta tar underscore equals backslash frac 1152 backslash times 40 20.32 backslash approximate 2 comma 268 backslash text BTU slash HR kinsulated equals for total A times delta D is equal to 20.32115 2 times 40 almost equals 2,268 BTU slash HR. The insulated slab loses heat at roughly 3% of the rate of the uninsulated slab. This is not a minor improvement. It is a difference between a structure that is thermally coherent and one that is hemorrhaging energy through its floor, while the builder stands at it puzzling over why his consumption is twice his estimate. But Harold was not finished with the slab system. The XPS board alone addresses the thermal break. It does not address the structural problem of a slab that floats, meaning a slab that is not anchored to ground by footings and therefore must resist lateral loads from the arch above through its own mass and the friction between its undersurface and the foam board. A floating slab, unlike a conventional foundation, has no footings extending below the frost line. It sits on its insulated subbase and is intended to move as a unified monolithic unit if any ground movement occurs, rising and falling with frost heave as a single piece rather than as a collection of differential settling elements. The engineering requirement for a floating slab is therefore that the concrete itself must be strong enough to resist cracking under the bending loads that occur. The ground beneath it is not perfectly uniform in its support. Harold designed the slab to meet this requirement through 3 specific measures. First, the concrete mix specification. Harold used a 5,000 psi mix, stronger than the standard 3,000 to 3,500 psi residential specification. The higher compressive strength comes primarily from a lower water-to-cement ratio, which also reduces porosity and therefore reduces the slab's susceptibility to freeze-thaw spalling on its edges, where exposure to moisture and temperature cycling is highest. Second, the reinforcement schedule. Rather than standard 6x6 welded wire mesh, which is a minimum acceptable reinforcement for residential slabs and which Harold describes, without particular heat, as better than nothing and not much else, he specified a grid of number 4 rebar on 12-inch centers in both directions, placed at mid-depth in the slab. Number 4 bar is half-inch diameter steel, with a yield strength of 60,000 psi. A grid of it on 12-inch centers at mid-depth in a 6-inch slab provides genuine flexural resistance, the ability of the slab to span across a soft spot or void in the subbase without cracking. Harold calculated the design bending moment the slab might experience if a 4-foot by 4-foot area of the subbase were to lose bearing support entirely, a worst-case scenario he considered worth designing against. The maximum bending moment in a simply supported slab spanning 4 feet under its own weight plus a distributed floor load of 40 pounds per square foot is max equals WL28M underscore max equals backslash frac W backslash L square 8 max equals AWL2, where WW. W is the distributed load per linear foot and LL. L is the span. For a 12-inch wide strip of slab, W sad phase 150 PCF times 0.5 feet plus 40 times 1 equals 115 lb slash FTW equals 150 backslash text backslash times 0.5 backslash text FT plus 40 backslash times 1 is equal to 115 backslash text LB slash FT. W sad face 150 PCF times 0.5 feet plus 40 times 1 equals 115 lb slash foot over a 4-foot span. Max equals 115 times 168 equals 230 FTLB per foot with M underscore max equals backslash frac 115 backslash times 68 equals 230 backslash text. FTLB per foot of width max is equal to 8,115 times 16 equals 230 FTLB per foot of width. The number 4 bar at mid-depth in a 6-inch slab provides a design moment capacity of approximately 450 foot-pounds per foot of width, giving a safety factor of roughly 1.95, acceptable for this application. Third, and perhaps most importantly for the long-term performance of the system, Harold specified fiber reinforcement added to the concrete mix. Polypropylene fibers at a dosage of 1.5 pounds per cubic yard. These synthetic fibers do not significantly increase the slab's structural strength. That is the job of the rebar, but they dramatically reduce the formation and propagation of shrinkage cracks that occur as the concrete cures and dries. Shrinkage cracks in an unfiber-reinforced slab are essentially inevitable. They are typically hairline in width and structurally harmless, but in a cold climate structure, they are potential pathways for moisture infiltration, freeze-thaw cycling within the crack itself, and, particularly relevant in Harold's case, entry points for radon gas, which is present in the Matanuska-Susitna Valley at levels that require attention in below-grade and slab-on-grade construction. The fiber reinforcement worked. When Harold stripped the forms and examined the slab surface at 28 days of cure, the standard test age for concrete compressive strength, there were no visible shrinkage cracks. A core sample sent to a laboratory in Anchorage returned a compressive strength of 5,340 psi. There was one additional element of Harold's foundation system that we observed during our site visit, and that deserves specific attention because it represents a solution to a problem that most builders do not recognize until after it has already damaged their structure. This is the question of the thermal bridge at the slab perimeter. A floating slab, insulated from below, still has exposed edges. If those edges are uninsulated, if the concrete is directly exposed to ambient air at the perimeter, then the edges become a thermal bridge, a low-resistance path through which heat conducted from the warm interior of the slab can escape directly to the cold exterior air. The delta T backslash delta T. Delta T at the perimeter of Harold slab on a minus 40 day is 68 degree F minus 47 degrees Fahrenheit, equals 115 degree F 68 degree F minus 47 degrees Fahrenheit, equals 115 degrees Fahrenheit. 68 degree F minus 47 degrees Fahrenheit, equals 115 degree F. Heat loss through a thermal bridge is proportional to that differential. An uninsulated slab edge on a minus 40 day loses heat at a rate more than twice what would lose on a day when the exterior temperature is 0. Harold addressed this with a vertical skirt of 2-inch Type 9 XPS board installed on the exterior face of the slab perimeter, extending from grade level down to bottom of the slab. 6 inches of vertical insulation covering the full perimeter. This reduced the effective thermal bridge to the thin exposed strip at the very top edge of the slab, which is itself partially protected by the arch structure and the earth berm that eventually covers it. Measured with a thermal imaging camera on a day when the exterior temperature was minus 31 to 31 degrees Fahrenheit. Minus 31 degrees Fahrenheit. The surface temperature of the slab edge at a point where the perimeter insulation was installed was 24 degree F 24 degree F. 24 degrees Fahrenheit, cold, but not dramatically colder than the surrounding burned earth. At a point near the entrance end of the structure, where the perimeter insulation had not yet been installed at the time of the photo, the same camera recorded a slab edge temperature of 4 degree F 4 degree F. For degrees Fahrenheit, a difference of 20 degrees in surface temperature on the same slab on the same morning, representing an enormous difference in heat loss rate. The completed floating thermal slab, 24 by 48 feet, 1,152 square feet of interior floor area, 6 inches thick, 5,000 psi concrete with number 4 rebar on 12-inch centers and polypropylene fiber reinforcement, sitting on 4 inches of Type 9 XPS over compacted coarse gravel with perimeter drainage. Cost Harold $14,200 in materials and $3,800 in equipment rental for the excavator. He formed and poured himself with 2 friends over 3 days in August 2020. At the time of our visit, 26 months after the pour, there were no cracks visible on the surface, no evidence of differential settlement, and no measurable deflection at the midspan of the slab when Harold walked across it with a 90-pound pack. A test he performed for us with the calm precision of a man who had calculated the result in advance and was simply confirming it. The arch was erected on top of the slab in September 2020, before the first hard frost of that year. The Quonset kit Harold selected was a 24-foot clear-span ribbed arch system from a manufacturer in the continental United States, shipped by freight truck to the end of the road and transported by his own flatbed trailer, the final 7 miles to property. The arch panels are formed from 14-gauge galvanized steel, roll-formed into a corrugated profile, and then cold-formed into the arch curve in the field using a portable forming machine. Harold assembled the arch in 4 days, working alone. The arch kit came with anchor bolts for attachment to a concrete foundation, which Harold had embedded in the slab perimeter during the pour. The anchor bolt pattern deserves mention because it is part of the structural integrity of the system. Each arch rib terminates at the slab in a base plate, a flat steel plate welded to the rib and drilled for the anchor bolts. Harold used 5/8-inch diameter anchor bolts embedded 10 inches into the slab on 18-inch centers around the full perimeter. The connection of the arch to the slab must transfer both the vertical reactions from gravity loads and the horizontal thrust that the arch exerts at its base. Because an arch, unlike a beam, pushes outward at its base as well as downward, and if that outward thrust is not resisted, the arch will spread and eventually collapse. The horizontal thrust at the base of a semicircular arch under a uniformly distributed vertical load WW, W per unit of arch length, over a span LL. L is H equals WL28RH equals backslash frac W backslash L squared 8 backslash R H equals 8RWL2, where R is a rise of the arch, which for a semicircle equals L divided by 2L divided by 2. L/2, substituting. H equals WL28 L/2 equals WL4H equals backslash frac W backslash L squared 8 backslash L/2 equals backslash frac W backslash over H equals 8 L/2. WL2 equals 4 WL. For Harold's 24-foot span arch carrying a designed snow load of 60 pounds per square foot, the ground snow load for his elevation and location per the applicable ASC 7 provisions, plus the dead load of the arch panels and insulation, approximately 8 pounds per square foot, the total distributed load WW. W per linear foot of arch is W sad phase 60 plus 8 times 24 equals 1. 632 lb/ft of arch length equals 60 plus 8 backslash times 24 equals 1 comma 632 backslash text lb/ft of arch length W sad phase 60 plus 8 times 24 equals 1 632 lb/ft of arch length. H equals 1 632 times 244 equals 9 792 lb/ft of arch perimeter H equals backslash frac 1 comma 632 backslash times 244 equals 9 comma 792 backslash text lb/ft of arch perimeter H equals 41 632 times 24 equals 9,792 pounds per ft of arch perimeter. This is approximately 4.9 tons of horizontal outward thrust per linear foot of arch base, a force that the anchor bolt system must transfer into the slab, and that the slab must transfer into the subgrade through friction and bearing. Harold's calculations show that the friction force available between the 1,152 square foot slab and the compacted gravel subbase, using a conservative friction coefficient of 0.4 for concrete on gravel, was more than adequate to resist the total horizontal thrust. He also noted correctly that the earth berm that would eventually cover the sides of the arch to a depth of 4 feet will provide passive resistance against arch spread, acting as a retaining force distributed along the lower half of the arch perimeter. At the time of our most recent visit, in February of this year, with the exterior air temperature recorded at -47 to 47 degrees Fahrenheit, minus 47 degrees Fahrenheit at 6 in the morning. The interior temperature of Harold's completed Quonset, fully insulated, bermed to a height of 52 inches on 3 sides, with a floating thermal slab, closed-cell spray foam on the interior of the arch to a depth of 5.5 inches, and a central wood-burning masonry stove fed twice per day, with 71 degree F, 71 degree F, 71 degrees Fahrenheit. The delta T backslash delta T. Delta T between interior and exterior was therefore delta T equals 71 degree F minus 47 degrees Fahrenheit equals 118 degree F backslash delta T equals 71 degrees Fahrenheit minus 47 degrees Fahrenheit equals 118 degree F delta equals 71 degree F minus 47 degrees Fahrenheit equals 118 degree F. Harold with consumption for the month of January, during which the mean exterior temperature was minus 31 to 31 degrees Fahrenheit. Minus 31 degrees Fahrenheit was 0.6 cords of birch. His consumption in the old spruce cabin during a January comparable mean temperature was 1.4 cords. The reduction in fuel consumption is 57%. The improvement in interior temperature from a mean of 58 degree F, 58 degree F. 58 degrees Fahrenheit in the cabin to a mean of 71 degree F, 71 degree F. 71 degrees Fahrenheit in the Quonset is 13 degrees Fahrenheit of additional warmth, achieved at less than half the fuel cost. He keeps a logbook. He has kept a logbook since he first moved onto property in 1987. Every morning at 6, he records the exterior temperature, the interior temperature, and the amount of what he consumed in the previous 24 hours. The logbook from the cabin years fills a shelf. The logbook from the Quonset years fills a quarter of a single binder. We asked Harold whether he thought about the old cabin often. Now that it was gone, he had disassembled it the summer after he moved into Quonset and burned the logs that were not worth salvaging. He considered the question for a moment in the way that he considers everything. I think about the foundation, he said. I think about it fairly often. I should have looked at what the soil was doing years earlier. I was an engineer. I had the tools to read it. I just didn't look. He refilled his thermos and did not elaborate further. Outside, the temperature at that hour was minus 44 to 44 degrees Fahrenheit. Minus 44 degrees Fahrenheit. The arch stood in the clearing among the spruce trees, half buried in earth and snow. Nothing about it particularly remarkable to look at. Just a curve of corrugated metal disappearing into a hillside. Inside, the stove ticked quietly in a way that cast iron ticks when it is working. The floor, 6 inches of reinforced concrete floating on 4 inches of foam, floating on 12 inches of compacted gravel, over a French drain system that had not allowed a drop of water to reach the soil column beneath the slab in 2.5 years, was warm underfoot. This is the engineering. Not glamorous. Not fast. Each decision made deliberately, traceable to a calculation, defensible in numbers. The floating thermal slab is not one idea. It is 5 ideas working simultaneously. Drainage management, frost heave mitigation, thermal resistance, structural redundancy against differential settlement, and perimeter thermal bridging control. Remove any one of the 5, and the system is compromised. Keep all 5 in the ground, which has been trying to destroy structures built on it in this valley for as long as there have been structures, simply has no mechanism by which to do so. Harold Messing is 74 years old. He plans to stay.